Hi everybody, welcome back. This is going to be the last part for chapter 25. We just have a small topic of the dielectric materials that we need to discuss. And this will actually go pretty quick. We only need to do one derivation, and then we can show how that's going to relate to all of the other case scenarios that we have out there. But I want to bring our attention back to the expressions that we came up with for the different types of capacitors. We had the parallel plate capacitor, we had the cylindrical capacitor, and then the spherical capacitor. And so I'm going to go ahead and just write out the expressions that we had for each of these. And let's see, for the sphere, that was 4 pi epsilon naught AB over B minus A. All right, so for the parallel plate capacitor, A was the cross-sectional area of the plate, D was the separation distance. And then for the cylindrical case and the spherical case, little a and B were the inner and outer radius values for each case. So we had radius A, radius B, radius A, radius B. So each one of these derivations were based on the idea that there was nothing in between the layers of our capacitance surfaces. In other words, each of our conducting surfaces was separated by vacuum or air. And as a result, we've been using epsilon naught to take that into account. Now we want to see what happens if we replace the vacuum between the plates with something else. And so I'm going to fill in the area between the plates here with some material. Don't know what it is exactly. All I know is that this material is non-conducting. So in other words, we have an insulating material here. Otherwise, if we allow it to be an insulator, or if we allow it to be a conductor, then any charge that is built up will just go from one side of the capacitor to the other. And so now that we have this material in there, we're going to call this material our dielectric material. And this material, just like any other material, it has charge in it. It's just that that charge is a combination of positives and negatives, which are producing a net null charge of 0. But now that we have the high concentration of charge on either plate of our capacitor, and this charge will have come from a battery most likely. But now that we have that charge there, it is possible that some of the charges that produced the null charge could separate and be partially attracted to the two plates of our capacitor. Now again, this is an insulating material, so the charge cannot move enough that it would conduct to one of the plates. But it is still possible that a little bit of that charge could migrate. And so there might be a little bit of charge inside that insulating material that is able to separate and kind of migrate its way towards the plate of the opposing charge. And so what this separation of charge within the dielectric material does is it provides us an opportunity to redo the derivation for the capacitor system. So we've already seen this derivation once before with the parallel plate capacitors, and we said that in order to define the capacitor, we needed to know the charge to potential ratio. But in order to do that, we had to know the difference in potential across the two plates of the capacitors. Now again, you might be saying, well, if you hook it up to a battery, wouldn't you know that? And the answer is yes, but no capacitor should be defined by the battery that it's hooked up to. Every one of these capacitors should already have its store-bought value predetermined before we plug it into something. And so we need to follow this path through the derivation to help us figure out can we rewrite this ratio expression in terms of geometry and materials properties, because we now are including a very different material between the two plates, and we need to see how that's going to affect the electric properties of this capacitor system. And so we actually had to go all the way back to chapter 23 and set up Gauss's law to tell us what the electric field between the two plates is going to be, so that we could plug that into our change in potential expression, so that we could plug that into our chapter 25 expression defining the capacitance of our system. Now, I do want to make clear that the separation of charge within our dielectric material is not going to be equal and opposite to the charge that is on the plates of the capacitor. Okay, we're not going to be able to shift that much charge around inside this dielectric material. And so I'm going to call the negative amount of shifted charge negative Q prime. And that prime is just there to indicate that this is a different value from what is on the plate of the capacitor. This is not a calculus notation. And because our null charge has to separate in equal and opposite amounts, then we would have a positive Q prime that would migrate towards the negative plate of the capacitor. And so the overall magnitude of charge that is sitting on either of the capacitor plates is going to be larger than the shifted charge within the dielectric material. All right. Now the reason we have to specify that is because if we look at the Gaussian surface that we've drawn through here, because again we want to know what are the electric field lines that are going to be produced between these two plates. I need those electric field lines to pass through the surface of our container. And everything is actually going to go exactly the same as the way it did when we had the capacitor with nothing in between the plates. The only difference now is that the enclosed charge is the difference in the charge value on the plate versus the migrated charge within the dielectric material. And that is how we're going to set up Gauss's law for this system. As I said, everything else is gonna go exactly the way that it did before. So if you want to check back in your notes, we take the enclosed charge And after we took care of the dot product, the electric field between the plates was said to be uniform. All that was left was to integrate about the surface that the fields passed through, but that was just going to be the surface area of the capacitor plates themselves. And so everything here should look very, very familiar. For our dielectric system, this is the electric field between the two plates. So we'll go ahead and label that as the electric field for the dielectric system, versus for the empty plates, so the capacitors that did not have any material between them, this was the expression that we got. But we're not using that anymore. We have to use this. And so this is going to go into our difference in potential expression. The author had this thing about integrating from the negative plate up to the positive plate. And in doing so, the displacement vector ds pointed in a direction that was opposite of the electric field vector. And that resulted in a -1 when we evaluated the dot product. And that just turned the minus sign out front into a positive. We then bring in our electric field expression, which upon further inspection does not depend upon the change in position between the two plates. And so that electric field expression could come outside of the integral. And the evaluation of our integral ds going from one plate to the other, well, the two plates were separated by a distance of d. And so that's what our integral of our displacement is going to evaluate to, is ed. And this is the same outcome that we came to with the empty capacitor. The only difference is now when we plug in the electric field expression, we're still carrying along the difference in the charge values. So this is the change in the electric potential as we move from one plate to another. And as we said, that change in potential needs to go into the capacitor ratio expression. And here's where we really see things start to get different. This charge value right here, this is the charge that sits on the plate of the capacitor. This is the charge that is sitting on the plate of the capacitor. That charge will have to now be compared against the charge difference between the plate and the migrated charge within the dielectric material. And in this case, I no longer have the option of just canceling out the charges, because up here I have some value of charge Q. Down here I have a different value of charge. So I can't just cancel them out anymore. What happens as a result of this is that we still get the same sort of generic outcome as what we had before. So if we take this expression that we got for the dielectric capacitor, and if we compare that against the expression that was derived for the empty parallel plate system, well, this is the empty plate system. And this is what we got for the capacitor that actually had some material between the two plates. The only difference between the two expressions is this charge ratio. And we might be thinking to ourselves, well, how easy is that going to be to measure the charge ratio between the plate and the stuff that's moving around inside that dielectric? And it's not going to be that easy. But we don't necessarily have to measure that ratio. We can measure the effects. If we take our dielectric capacitor and compare that to a parallel plate capacitor that has the exact same dimensions, so this is our dielectric capacitor, and this is the empty parallel plate capacitor, which has the same dimensions. So really all I have to do is just build the thing, measure the capacitance values of each individually, and the ratio of the two will tell me what the charge ratio within that dielectric material is. And we take this ratio and we give it a name. We call this kappa. This is the dielectric constant of the material. So whatever material it was that you placed in between the plates of your capacitor will have a certain dielectric constant, or in this case, it will have a certain charge ratio. The greater the difference in the charge between the plate and the migrated values, the greater this value is, the smaller the denominator becomes. And the smaller the denominator becomes, the greater the quotient becomes. And so if we have a capacitor with a dielectric material in between the plates, I'm now going to take the charge ratio out and I'll replace it with kappa. Well, the greater that kappa value is, the greater the value of the capacitor that I'm going to be able to build. Now, we're still using epsilon naught in here. And you might be thinking to yourself, well, I thought he said that once we put a new material in here, we were going to have different behaviors based on that material, because epsilon naught was supposed to be for air or vacuum. And that is correct. This new material, this new dielectric material, will have its own unique permittivity value, epsilon. So let's give a name to this material. Let's say this was a piece of glass. So all this purple stuff in here is glass between the two plates of our capacitor. So there would be a unique permittivity value for that glass. Now there are plenty of different mixtures and formulas for glass, and so each one of those would have a slightly different permittivity value. But it doesn't even have to be glass. It could be some kind of plastic or a polymer or a block of wood, as long as it's not conductive. Well, so how does this new permittivity value compare to epsilon naught? And we kind of just answered our own question. The permittivity of glass is going to equal the ratio of the two terms. Or actually, I kind of misspoke there, but the dielectric constant of the material is going to equal the ratio of the permittivity for that material versus the permittivity for air and vacuum. But this means that we don't really need to look up the permittivity for the glass. We can just look up the dielectric constant. And it's actually more beneficial to us to use the dielectric constant, because now think back to all of the different discussions that we've had throughout the semester where epsilon naught shows up. And the first time that this showed up for us was with electrostatic force between two charges with Coulomb's law. With Coulomb's law, we said the force between two charges was equal to K, Q1, Q2 over R squared. Well, this K right here, this lowercase k, this was the 1 over 4 pi epsilon naught term, which we've been writing out in its full form. So you've got two charges that are sitting out in space, and as long as there's nothing in between them, then this is how the force will behave between those two charged particles. So let's put charge 1 and charge 2 out there in space, and there's nothing in between them. It's just air or vacuum. And so this is how those two charges will behave in terms of their respective forces. But now we place a block of glass between those two charged particles. How is having that block of glass between the two charged particles going to affect that electric force that is operating between them? Well, this piece of glass has a different permittivity value. We can either go in and replace every single epsilon naught that we've been using throughout the semester with a different epsilon value for glass, which in turn would change the value of K, or we can just take the kappa value, or the dielectric constant, that is associated with that material, and we just pair it right along with epsilon naught. So anywhere in any of our previous equations where epsilon naught has shown up, if we want to update these equations to consider dielectric materials, then all we have to do is look for where in the equation that epsilon naught value is at and pair it with the appropriate dielectric constant for that material. In this case, the dielectric constant of glass. So what are some of the other equations that were out there? I think we had there was the electric field of an infinite sheet, and that was like sigma over 2 epsilon naught. Okay, so you have an infinitely large sheet of charge, and the electric field above it would be that. But that's only if there's nothing between the sheet and the point in space where you're trying to measure things. Now, put a sheet of glass between the point where you're trying to measure things and, sorry, let me try that again. Let's put a sheet of glass between that infinite sheet and where you're trying to measure things. Well, how do we find the electric field now? We just need to incorporate that dielectric constant with epsilon naught, and now we're done. Our equation has been updated for the dielectric constant of that material. Now, these dielectric materials, once we've placed that dielectric material in between the plates of our capacitor, we can take any of the previous equations and, believe it or not, we can go through and we can update every single equation just by incorporating the kappa value with epsilon naught. So we've got kappa and epsilon naught. We've got kappa and epsilon naught. We've got kappa and epsilon naught. Every one of those systems can be updated for a dielectric material just by introducing that kappa value. Very, very easy to do. Okay, one last bit for these dielectrics. I'm going to zoom in here because the highlighter option is getting kind of thin. You have a capacitor of cross-sectional area A and a separation distance of D. And you put a dielectric material in between the plates, but you don't quite have enough of this first dielectric material. You can only fill it in about halfway. Well, actually, we'll say exactly halfway for the sake of the math. So you've got your first dielectric material here. You fill half of the capacitor with that dielectric material. We'll call it kappa 1. And then you fill the other half of the capacitor with another dielectric material, which has value of what we'll call kappa 2. With two different dielectric materials in there, kappa 1 does not equal kappa 2. What would be the capacitance of the structure? Well, it is a parallel plate capacitor, and so an empty parallel plate capacitor would have this for its capacitance value. And if it were completely full of just one type of dielectric material, then we would just have to pair that kappa value with epsilon and we would be done. Not quite what we have though. We have two different materials, and what I would like to do to help us in figuring this out is I'm going to redraw the picture in such a way that instead of having one capacitor with two dielectric materials in it, I want to draw two capacitors that are, for all argument's sake, inseparable at the intersection between the two dielectric materials. So I have one capacitor which is on the top, made of material kappa 1, and directly in contact with that is a second capacitor made of material kappa 2. So I just have this black line here as an indicator of the separation of the two materials. So if you need to think of this as a very, very, very thin sheet of conducting material, so be it. But that basically means that I now have a two capacitor system that is connected in series. And that I can work with because each capacitor would have a cross-sectional area of A, And because each dielectric material is taking up half of the volume, we could say that each capacitor has a separation distance of d over 2. From here, we can define two distinct capacitance values for each capacitor, and then we can combine them in series. So for the kappa 1, kappa 2 materials, for the kappa 1 portion, I have dimensions of A for area, d over 2 for separation distance. We have epsilon naught, which will be paired with our kappa 1. And that would be the value of the first portion, which we're going to call capacitor 1. Needs to be a little bit of cleanup here. The d over 2 will turn into a 2 kappa epsilon A over d. That's kappa 1, sorry. Then we'll try the same thing with the second dielectric material. We're going to use that to construct the second capacitance portion, which is going to look very similar. And those are the values of capacitance that each individual portion will provide. It is our job now to put them together into a single expression. The capacitor values are connected in series, and we know that we can take two capacitors connected in series and we can combine them using the inverse summation approach. Capacitor 1 has this for its capacitance value, 2 kappa 1 epsilon naught A over D plus 2, which is 2 kappa 1 kappa 2, sorry, over D. I'm going to go ahead and bring the displacement values up to the top. So we have D over 2 kappa 1 epsilon naught A plus D 2 kappa 2 epsilon naught A. There's a lot of common terms in each. We can factor out D2 epsilon naught A from each. And we're left with 1 over kappa 1 plus 1 over kappa 2 equals 1 over equivalent. Now, I know we're waiting to flip that over, but before we do that, we need to combine our kappa values. To do that, we need a common denominator. That means we need to cross multiply between the terms. We have kappa 2 plus kappa 1 all over the combination of the kappa values. We have 2 epsilon naught, or D over 2 epsilon naught A in the front. And now everything can be flipped. So what do we have now? We have 2 epsilon naught A over D, kappa 1, kappa 2 over kappa 2 plus kappa 1. And that would be the capacitance value of this construct. Now, that was a little intense in terms of the algebra, but that's because I kept going and I wanted to get a final value for the equivalent capacitor, but I just as easily could have stopped at this line right here, because what would you have to do if there was a third material that were added? What if instead of these two materials taking up half of the thickness of the capacitor, what if there was a third material and each material was taking up a third of the total thickness? Well, in that case, you would end up with a third kappa value in your algebra, along with a 3 in these steps here. But you know what? Let's not go there. If we need to, we can figure that out in a future problem set. But basically what we have here is that 1 over the equivalent capacitance for our circuit is going to equal d over, this 2 came from the fact that we had to divide the thickness into those appropriate segments. So I'm going to say n, where n is the number of distinct equal portions that we have to break things up into. And then we have the summation of 1 over the individual kappa values as we go from 1 to n. Well, that works great if the dielectric materials are stacked one on top of another. What if your dielectric materials are staggered side by side? So now we have half of our capacitor that is filled with one kind of dielectric material, and then we have the other half which is filled with some other dielectric material. And again, we'll just go half and half with the two pieces. Call this kappa 3 and kappa 4. Now each of these is filling the full depth of the capacitors, but they only take up half of the surface area. And as you can probably see, what's going to happen, having these two capacitors side by side is like having two parallel capacitors that are really, really close to one another. The one stipulation that we need to use the parallel case scenario is that each capacitor has to have the same potential difference across their plates. Well, that is no problem whatsoever because they're both part of the same physical construct. All I need to do now is figure out, this should be 3 and 4, not 1 and 2, sorry. All I need to do now is figure out what would be the individual values of these two capacitors, and then I can combine them to produce an equivalent, which in the case of parallel capacitors, all I have to do is add them directly. Okay, here we go. The parallel plate capacitor would have just a regular epsilon naught A over D times the appropriate kappa value. So in this case, it would be kappa 3. Now, I am using the full depth of the capacitor, but I'm only using half the surface area. So I need to incorporate that into the equation for C3. Likewise, I have kappa 4, epsilon naught A, D, except we're only using half the surface area, and that is C4. So kappa 3, epsilon naught A, we have 2 and d in the denominator, kappa 4 epsilon naught a, 2 and d in the denominator. This is capacitor 3 plus capacitor 4 equals equivalent capacitance. But all that we get out of this is basically a direct summation of the individual kappa values. And so our equivalent capacitance here is epsilon naught a over, and again, this 2 comes from the fact that we're segmenting the area into equal portions. So if we do that for larger segments, we would have to divide by n, and then take the summation of each individual kappa value as we go from 1 to n. But we're really not going to see a whole lot of examples of these complex dielectric systems. These are really just here for, dare I say the word fun, but in showing us how we can produce different capacitance values using combinations of different materials. And then, if I really wanted to be mean, I could put together something like this, where you would have, multiple dielectric materials, and ask you what would this capacitance value be if you took your capacitor and plugged in different dielectric materials of different volumes. And you could do this without too much hassle. You would just have to take it a step at a time, and combine these two in parallel. You could combine these two in series, and then you could take the combination of the two in parallel, and then you would have the equivalent capacitance of that dielectric construct. Again, I really can't see of any reason why you would want to do this in application in a real world scenario, but you could if you wanted to. So I'll leave that to you and any of your future coursework and your professors, if you ever end up working with dielectrics of any case and producing capacitors. Now you know how to do that. So that finally brings us to the end of our chapter 25 material. We now know how to deal with dielectrics, not just with our capacitors, but for any kind of system where epsilon naught shows up, we can update the expression for that system simply by including the kappa value for that dielectric material. So that's it. We'll see you at chapter 26.